Welcome back, fellow physics enthusiasts. Well, today I'm just going to pick up right where I said I would last time and show how to derive these equations of motion using only calculus. And as you will probably see here, this video is going to be a lot shorter, given the fact that calculus is probably the most efficient way of going about this. Hence why Isaac Newton probably invented it for this reason. So, let's begin. All right, so to begin, we're just going to start out with a familiar equation. And if you're not familiar with it, it's no big deal. We're simply just extracting one simple variable from it. And that equation is none other than the infamous Newton's second law, which is F is equal to ma. And the variable that we want from this is the acceleration, because the acceleration is what provides the force. But that's a topic for another discussion. So, what is acceleration? Well, we had established before acceleration is simply the change in velocity per unit time. So we will express that using calculus notation this time. So dv over dt. So let's bring that dt over and go from there. So a dt is equal to dv. Now at this point, we're going to employ some integrals where we integrate both sides here. We have two definite integrals where this side goes from 0 to t, and this side is from v initial to v final. Now let's carry out that operation where on the left side we have simply at equal to, on this side, v final minus v initial. Now we'll bring that v initial over. So v final is equal to v naught plus at. And there we have it, Newton's first equation of motion. Okay, so now let's start deriving the next one. So this time we're going to define what velocity is. So velocity is simply the change in position over the change in time. Now let's bring that dt over. So v dt is equal to dx. Now at this point, we aren't going to integrate right away, but what we are going to do is plug this v in, this equation in for this v. So what do we have? So we're going to have v initial plus at times dt is equal to dx. And now we can integrate both sides. So like we always do, start from 0 to t. And here, start from our initial position to our final position. Okay, so let's carry out this operation this time. So on this left side, we're going to have v naught times t. Carry that t over to this side now. Since we have a t on this part of the equation, we are simply just going to do this. So t1 plus 1 over 1 plus 1 equals t squared over 2. So now that leaves us with 1/2 at squared. And that is going to be equal to our x final minus our x initial. And we can just simplify that a little bit, make it look nice and pretty, where delta x is equal to v naught t plus 1/2 at squared. And there we have it, Newton's second equation of motion. All right, and now for the third equation of motion. Now this one requires a couple more steps, but it's no more challenging. So how do we do that? So we are going to define velocity and acceleration again. And this time we're going to put them in terms of t, because as we established in the previous video, this is the time-independent equation. So we can't have that in our equation here. So we're going to have, so v is equal to dx over dt and then A is equal to dv over dt. Now, we can put this in terms of t for both of them. So for acceleration, we're going to have dt is equal to dv over a. And then for this one, we're going to have dt is equal to dx over v. And at this point, we can just set these two equal to each other. So we're going to have dv over a is equal to dx over v. And now we can just cross multiply. So we're going to have v dv equal to a dx. And at this point, we can now integrate both sides. So we're going to have v initial to v final, x initial to x final. All right, so let's carry out this operation again. We're going to have, I'm just going to do it over here. So we're going to have, so v initial position, final, we're going to have v squared over 2 is equal to a times our final position subtracted from our initial position. So x final minus x initial. Okay, let's carry this out. We're going to have v final squared minus v initial squared. And this is all going to be multiplied by 1/2. And that's going to be equal to a delta x. Now let's just simplify this a little bit. We're going to have our v final squared equal to our v initial squared plus 2a delta x. And there we have it, our time-independent equation right here, yet again. One final magic erase. And there we have it, our 3 equations of motion expressed using only calculus. And as you can see, based on the length of this video, this was a lot more efficient and required a lot less explanation, yet it was possible one way or the other, as you could see. So if you have any further questions, please reach out to me and I will elaborate in any way I can. Thank you.